Now we are going to discuss about shrinkage. The creep and shrinkage are more or less the same. Again, this shrinkage is also related to gel pores. Here also we will be exhibiting the same phenomena as like that of the creep. Here also we can see, because of the movement of water from gel pores to capillary pores, the shrinkage occurs. In general, in concrete, shrinkage occurs due to hydration process. In general, in concrete, the shrinkage occurs due to hydration reaction, that is the loss of water due to evaporation, both in plastic and dry state. Because of this loss of water due to evaporation, we exhibit some change in the volume, and that is termed as shrinkage. The types, let's discuss about the types of shrinkage. Chemical shrinkage. This chemical shrinkage occurs during the hydration reaction, since at the initial stage of hydration reaction, the volume of hydrated cement will be less when compared to that of the unhydrated portion, and there comes this chemical shrinkage. Next, autogenous shrinkage. It is the macroscopic reduction in the volume, that is, in a sealed specimen, no water will be allowed to enter or leave the specimen. In that condition, if we exhibit some volume change, then that is termed as autogenous shrinkage. That is, this arises mainly because the plastic, the ingredients which is in the plastic stage are being converted into the solid stage. Because of this because of this transition, there exhibits a reduction, and that reduction is called as autogenous shrinkage. Third is plastic shrinkage. This plastic shrinkage occurs when a concrete is in the plastic stage, that is, assuming this to be the concrete. After concreting, because of having a low specific gravity, the water will move up, leaving the aggregates and cement paste down, and this, if this bleed water gets evaporated, then there occurs a plastic shrinkage. Fourth one is drying shrinkage. It occurs in hardened concrete. This drying shrinkage occurs in the hardened concrete. That is because of the movement of the gel water from pore. There will be some breaking of bonds. That is we have discussed in the first lecture. We have discussed this in the hydration part. That is the bond which exists between the cement products is of van der Waals force. So because of that breaking of bonds and creation of another bond, this drying shrinkage occurs. And the last one is carbonation shrinkage. This carbonation shrinkage will form because of the atmospheric carbon dioxide reacting with calcium hydroxide. It tends to form calcium carbonate plus water, and this calcium carbonate will occupy less volume compared to calcium hydroxide, and because of this difference in volume, this carbonation shrinkage occurs. And again, the mechanism of shrinkage is also unclear, but it is related to movement of gel water, adsorbed water or interlayer water. The movement of the water from the gel causes a reduction in the volume of the gel, and that results in the shrinkage of concrete. That is because of the movement of the water from the gel, the capillary tension is set within the pore, and to compensate this, the calcium silicate hydrate skeleton, because of the movement of the water from the gel, there arises a capillary tension, and to balance this tension, a compressive force from the CSH gel is being induced, and because of this difference, shrinkage, that is volume change, occurs. Because of the movement of water from the gel pores, capillary tension occurs. To compensate this tension, balancing compressive force from CSH skeleton will come, and because of this a volume change will occur, and that is termed as shrinkage. Again, the factors influencing shrinkage. First one is modulus of elasticity of aggregate. If supposing this is my aggregate, this is the paste, if suppose I am having a higher modulus of elasticity of aggregate, then the shrinkage of paste, this paste shrinkage will be restrained by the aggregate. If not, then this paste shrinkage occurs and it ultimately results in the shrinkage of the concrete. So the modulus of elasticity of aggregate which I am using in concrete should have a higher value to restrain the paste shrinkage. Next is volume of aggregate. If I am having more volume of aggregate, then that concrete exhibits relatively lesser shrinkage when compared to that of a low volume aggregate content. And also, if water cement ratio increases, shrinkage increases, water cement ratio decreases, shrinkage decreases. This is because if water cement ratio increases, there will be more capillary pores and the movement of water from the pores will be more. So the shrinkage will be obviously more. If I am having a less water cement ratio, my shrinkage also will be less. Time and relative humidity. This is a shrinkage. %, relative humidity. This is 70% and this is 50%. And with respect to age, the shrinkage reduces, and also with respect to the relative humidity, my shrinkage varies. If I am having 100% relative humidity, then that specimen is exhibiting lesser creep when compared to 50 and 70%. If it is a fully saturated specimen, then there arises a decrease in creep, that is the swelling occurs, whereas if it is a 50 or 70%, then there will be movement of water from gel pores to capillary pores, and because of that there exhibits a little shrinkage compared to that of the 100% relative humidity specimen having 100% relative humidity. And next is volume to surface area ratio. Volume to surface ultimate shrinkage if I am having high volume to surface area ratio, less shrinkage, that is, if my surface area decreases, then the chance of evaporation will also gets decreased, and because of that I will be exhibiting lesser shrinkage. And if I am having low volume to surface area ratio, more shrinkage occurs, since I am having a larger surface area where there arises a chance for more evaporation compared to that of less surface area. So the shrinkage will be more when I am having low volume to surface area ratio, and these are the factors which influence the shrinkage in a concrete.